So we're going to, chapter 3 is all about graphing these trig functions. We're going to start by talking about graphing sine and cosines functions. Before we dive into that, though, I want to just recall a couple of important ideas from chapter 1. So if I have a function that I'll refer to as the parent function, I can transform that parent function algebraically in this following way. Right? That's how to transform an equation. Everybody's cool on that? Remember that guy from before? And I also have a graphical way to transform them. So if I take a point from the parent function, I can transform it to a point in my transformed function by doing that. So one of the main things we'll be doing here today is just kind of applying these ideas to graphing or writing the equations for these sine and cosine functions. Okay with that plan? So again, we'll be using those two ideas there throughout. What we'll do next is just kind of a little bit of an information dump. So we're gonna kind of complete this chart together. I'll give you a minute if you need to, for those of you that are following along, writing stuff down, to draw in your chart, because it's kind of a lot of stuff to write. But we'll kind of talk this through and follow this, or complete this together. Some of the words in this first column are things that you're familiar with, like domain and range and symmetry and continuity. Some of the other words are things that maybe we haven't explicitly defined yet, like amplitude, midline, period, and frequency. But we'll describe what those things are if you're not already aware of them in just a few minutes. But we're going to complete this chart here together. Okay, so let's do the sine column first. So the domain for a function, we remember, is the set of inputs that give us an output. One of the big outcomes from chapter 2 was that we took our definition of sine from outside of a right triangle and moved it onto the unit circle. So the input for sine is an angle measure, and to find the value for sine, the output of sine on the unit circle, we just find where the terminal side of that angle intersects the unit circle. And because we defined the standard position angle, we have angles of as big as we want or as small as we want, depending on which way we're rotating around around the XY axis. And regardless of how I draw that angle, it's going to intersect the unit circle somewhere, right? Everybody agree? So what does that tell me about the domain? If every angle that I can draw is going to intersect the unit circle, it means every angle has an output for sine. So the input is all real numbers. Everybody's okay with that idea? Okay. Let's talk about the range here. So the range, we remember, is the set of possible outputs. So on the unit circle, the outputs for sine are the y-coordinates. The smallest y-coordinate on the unit circle is -1. The biggest output is +1. And every y-coordinate in between -1 and +1 can be found. They are all, or there's a point on the unit circle that has the y-coordinate everything between -1 and +1. So that's my range. Keep in mind, though, when we write this, I'm going to use brackets as opposed to parentheses because, well, -1 and +1 are actual outputs of sine, right? Sine of 90 and sine of 270 give us the outputs of +1 and -1 respectively. Or if you prefer radians, pi/2 and 3π/2. Now let's talk about how we would actually go about generating then a graph of the sine function. So my inputs are the angle measures, and my outputs are the y-coordinates from the unit circle. So for example, 0 radians would output 0 for my value of sine. So the point 0, 0 would be a point on my graph of sine. Similarly, pi/2 is my input. 1 would be my output. So pi/2 and 1 would be a point on my graph. I could continue doing this. Pi 0, 3π/2 -1. And I could just kind of keep plotting these out. And I could use points in between. There's nothing special about the points I picked other than they're the extreme points, or the 0, or the x-intercepts. So they have that particular. But this is what the graph of sine looks like. And I could just generate this by plotting stuff from the unit circle, right? The angle measure with the corresponding value for sine are my x and y's, right? So basically the points here are theta, comma, sine theta. Typically when we graph things, graph sines and cosines, we use radians as our theta measures, mostly just for convenience, because if you're drawing an xy axis, it's a heck of a lot easier to go like from 1 to 6, which is about 2 pi, than it is to go from like 0 to 360, which is like, that's a whole heck of a lot of tick marks I don't want to mess with. So the standard is typically to use radians as opposed to degrees when we graph these things. Although you could still use degrees, but it's uncommon. So the next thing we have to look at is symmetry. If you remember back to chapter 1, one way of describing symmetry involved looking at the relative shape of the graph. So for the sine graph, I noticed that these parts that are like diagonal from each other with regard to the origin are basically reflections of each other. You guys see that? Do you remember what type of symmetry that corresponded to? Well, it's odd. And if I look at the graph that I drew, are there any breaks in the graph or jumps or asymptotes?
No.
No. So what does that tell us about the continuity? It's everywhere continuous, right? Everybody agree with that? Since there's no discontinuities there. So we're going to do the midline next. Okay, so when we talk about the midline for one of these graphs, we're talking about a line, well, a horizontal line that divides the graph kind of in half. So by dividing in half, I mean there's as much area trapped between the midline and the curve that's above the midline as there is trapped below the curve, or below the midline, I should say. Everybody cool with visually how to see that? So in the case of sine, it's pretty obvious that the midline is the x-axis, or y equals 0. Next up, let's look at the amplitude. The amplitude is a distance. It's basically the distance from an extreme point back to the midline. Or you could think of it as like the distance between, or half the distance between two of these extreme points. Same thing, right? So that is 1. That's the length. Everybody's cool with that? Okay. If we look at the graph again, we notice that this graph basically the shape repeats. So like if I start here, I have an up hump and then a down hump. And then it starts over where I have another up hump, another down hump. Graphs that have this kind of repeating behavior we call periodic. And we say the length of one of these non-repeating sections is 1 period. So in this case, going from negative 2 pi to 0, that's my horizontal length, is just 2 pi. That's how long that period is. Everybody's okay with that? So the period's a horizontal length. I guess I just said length. Let's be clear. So the period there is 2 pi. And the frequency is the number of periods per 1 unit length. So by definition, the frequency is just the reciprocal of the period. Cool with that? Let's look at the graph of cosine. Drop that in here real quick. Maybe I should label this one as sine also. I guess I kind of did when I labeled the point, the coordinates there, right? That's probably good enough. So I could generate the graph for cosine by kind of doing the same thing I did before by just pulling an angle measure and then the output for cosine to generate my points. Everybody's okay to do with that idea? It's not something I'd ever ask you to really do by hand. So I just wanted to explain kind of what's represented here. So just like the graph for sine, oh, wait, we didn't do any of the other stuff before that. Jeepers creepers. The domain. Got to be all real numbers, right? Again, every angle has an x value where it intersects the unit circle, so. And the range is going to be just like sines, because the smallest x value and the biggest x value are, the same. as this, because it's a circle, right? We cool with that? The symmetry, though, if I look at my picture, notice like it looks like it's a mirror reflection across the y-axis, right? Do you remember what kind of symmetry that was representative of? Yeah, it's a good guess because it's the only other option, right? You got it. And just like sine, there's no breaks or asymptotes or jumps or anything in our graph, so I know it's everywhere continuous. And then if I look at this graph of cosine, its midline is also at the x-axis. Its amplitude is also 1. The length of one period is also 2 pi. Everybody cool with that? Hopefully that's not surprising because everything is based on the same unit circle, right? Done.
So the amplitude, is that going to affect the range? So if the amplitude is like 2 on one of these?
Yeah, for sure. So let's talk about a transformation, right? When we talked about transforming a function, there's 3 different types of things we can do. We can reflect across the x or y axis. We can vertically or horizontally stretch or shrink. And then we can shift things up and down or left and right. Everybody agree with that? So let's think about the effect that those are going to have on domain, range, symmetry, continuity, etc. Okay? So we're going to do the second column for one of these transformations, or for each of these transformations. Everybody cool with that? Or the third column, I guess. Fourth column. Whatever, some column. The blank column. So domain. It was all real numbers before. If I stretch that, or vertically or horizontally, or we shrink it, or shift it left to right, up or down, can any of those, or reflect, can any of those things like tear a hole in the graph? Can any of those create an asymptote? So can any of them affect the domain? No, right? So again, the domain will remain unchanged for all sine and cosine functions as all real numbers. Yes? Sure. Now, Dom, you were onto something where the range certainly could be affected, right? So what 2 types of transformations can affect the range? Remember, the range is like the y-coordinate of the graph. Maddie? So a vertical stretch or shrink would make either the y-coordinates bigger or smaller, respectively. What else? There's another one. The horizontal stretches and shrinks are not going to change the y-coordinates. They'll change the location of where those y-coordinates occur, but the y-coordinates used will stay the same. Dom?
Transformation up or down?
Yeah, translation up or down. So if I pick up the whole graph and move it up, all the y-coordinates get bigger. If I pick up and move down, all the y-coordinates would get smaller, right? So here's my question. The vertical stretch or shrink is controlled by which coefficient? A, C, H, or K? A. And the vertical translation is controlled by which coefficient? K. Now, the A coefficient, is that an additive or multiplicative change? Multiplicative. The K is additive or multiplicative? Additive. So what we're going to end up with is K minus the absolute value of A to K plus the absolute value of A. So I have my new midline, and I can either go A units down from it or A units up from it. Everybody's okay with that idea? And we use the absolute value there for A because A could be positive or negative, right? And we want to make sure when we write our interval, the small number is first and the bigger number is second. So that's why there's an absolute value on the A there. It's just to ensure that it's properly formatted interval. Symmetry will likely be destroyed by any type of transformation, so we're not even going to worry about that. And if doing one of these transformations can't tear a hole or anything in the graph, obviously the continuity is going to remain the same. Can the amplitude be affected? Yes. What type of transformation is going to affect the amplitude? Vertical what? Stretch or shrink. Very good. Which was controlled by which coefficient? A, and that A operates multiplicatively. So my new amplitude would just be the absolute value of A. Again, the amplitude is a distance. The A can be positive or negative. That's why there's an absolute value tacked on there. Everybody's good with that? Okay. The midline, can that be affected? Yes. What type of transformation is going to affect the midline? Translating it up or down. What coefficient affects that? K. Is K multiplicative or additive? Additive. So K, or 0 plus K, is just going to be K. So my new equation is going to be y equals K. The period, can that change? Yes, good. What type of transformation is going to affect the period? Horizontal stretch or shrink, very good, which is controlled by C. And is that multiplicative or additive? Multiplicative. So it's going to be 2 pi times the absolute value of C. Again, C can be positive or negative, but the period is a length. That's why there's an absolute value around the C. And then the frequency is just the reciprocal of the period, so there's that.
So you just put all that over.
Yep.
1 over.
Yep, 1 over all that. I mean, even if you want to just say in general, like, just write 1 over period, you could do that too, right? If that's easier for you. Same thing. So far, so good. So these little formulas or whatever, you'll want to make sure that you kind of get familiarized with. Really only all you need to do is get this column down, right? Because the other column is just if, you know, the A and C are 1 and the K and H are 0. So don't bother memorizing all of them, just do the one column. You know what I mean? Cool. So the next thing we want to do is talk about, okay, how do we graph an equation then? So we're going to take an equation and want to generate the graph. Well, to do that, we're going to take some points from the parent function and transform them using this map that we mentioned earlier. The question we're left with is, what points from the parent function should I choose? Well, here's what I'm going to tell you. I'm going to tell you exactly which ones to choose. So for sine, you're going to use these 5 points. And for cosine, you're going to use these 5 points. Now, I have these things memorized because I'm like a crusty old math teacher that's done this like thousands of times. So it's like trivial that I remember these things. You guys, I would not expect to have this memorized. I would give you these things on a test or a quiz or whatever. Okay, So let's do an example where we actually generate a graph. Sound good? Okay. So here's my function that we're going to graph. So the first thing I want to do is I want to use the equation here that I'm given and pull the values for A, C, H, and K. So to do that, I'm just going to be relying on my general form for a transformation. The one thing I have to be careful about is this part inside the sign. Notice that in the red, the leading coefficient on x is 1. On the part in black, the leading coefficient on the x is 2. So before I go and I pull my values for A, C, H, and K, I'm going to need to factor that inside part in black. So I'm going to just factor off a 2. That's going to leave me with x plus pi over 2. Everybody's okay with that? So my A then is -2. My C then is 1/2. My H then is -pi over 2. And my K is -1. Any questions on how I got any of that? Take a look for a moment. If you're good, I'm good. Okay. So then I'm going to write my transformation map. So I have CX plus H, AY plus K. Notice that since H and K were negative, instead of writing plus and negative, I just wrote a subtraction. And what am I going to use that formula on? I'm going to use it on these key points from sine that I just gave you a moment ago. So far, so good? And I can just write down the resulting points, right? You guys get how to do that? If you need me to show it, it's fine, but it should be, all you're doing is plugging in x and y into the formula, right? Okay. Nobody's objecting, so I'm just going to go ahead and do it. Oops. If anybody does object now, I'm going to be like, come on, man. You know, like, where were you a minute ago when I asked? Come on. Oh my goodness. Okay. So let's go ahead and plot our points on this. This will be similar to what the worksheet format looks like that I'll ask you to graph in or graph on. So negative pi over 2 and negative 1. So notice each grid line is pi over 2, right? So this over here has to be negative pi over 2. That's negative 1. Negative pi over 4, negative 3. So negative pi over 4 would be halfway between negative pi over 2 and 0. So that's going to be like down there somewhere. 0, negative 1 is right there. Pi over 4, 1 is there. And then pi over 2, 1 is there. Or negative 1, excuse me. So if I draw my graph, it's going to look like that. Everybody so far so good? And then on a problem like this, I would ask you to fill the whole space, like have your graph fill the whole space. So I'm just going to kind of continue following my pattern now to fill everything else up. So the next spot would be a minimum, and then back to the midline, and then back to a maximum, midline, minimum, midline, maximum, midline, minimum, midline, maximum, midline, minimum, midline. And then just kind of connect things. So when we're extending a graph like this, I don't need to see the points written down. I just would want to see the points on the graph. You know, I don't need you to write anything down on the paper or whatever. Just make sure I can tell where the points are when you draw your graph. Is that okay on how I extended that? I just kind of followed the pattern that was going on. Which is the nice thing about a periodic graph, right? Is you can just keep extending forever and ever and ever if you want, just following the same old pattern. How do we feel about graphing? No biggie? Again, pretty straightforward, right? The hardest part is really making sure you get the correct values for AH or ACH and K, and then from there it's like just arithmetic, you know, like algebra or algebra 1 or pre-algebra type skills. So not too bad. Let's talk about the more challenging direction then. Let's talk about how we go from a graph to an equation. And this piece is not trivial. So let me cook up a quick example here, and then we'll walk through an example here together. That looks okay. Okay, so I went ahead and put a grid on behind the graph so it's a little bit easier to see where points are occurring at. So first things first, when we're going from a graph to an equation, there's infinitely many possible correct solutions. Okay. That doesn't mean that anything you write is going to be correct, but any correct answer has like infinitely many iterations. The reason being, just for example, if I shift to the right by 1 period, it's going to be the same thing. By 2 periods, it would be the same thing. 3 periods, 4 periods, 5 periods, all these would still look exactly the same. You guys can kind of see that? So right away, there's infinitely many answers. And for a graph situation, it doesn't matter whether you do your graph as a sine graph. I should say, if you use a sine equation, or if you use a cosine equation. We're going to solve this both ways. Is that okay? So we're going to do both. Okay. So for me to get a correct answer here, basically I just need to figure out values for A, C, H, and K that would generate these this graph. Everybody's cool with that? So I'm going to start by identifying the midline, because I can do that just visually. Looks to me like this is the midline. Everybody agree with that? So that is the equation y equals 1. So that tells me that k is 1. And the nice part about the midline is it's going to be the same whether you make a sine graph or you make a cosine graph. One coefficient down. That's not too bad. The next thing I like to find is the amplitude. So remember, the amplitude is the distance from a maximum and minimum back to the midline. So in this case, that amplitude is 2. Everybody agree with that? Starting at 1, going all the way up to 3. Yes. Are you somebody, Mr. Kulicking me? No. That's okay. And the nice part about the amplitude is that's going to be the same regardless. However, notice that the amplitude is not A, it's the absolute value of A. And it's very possible that one of these could be negative and the other one could be positive. So I'm not going to make that decision yet. Depending on how I find my H will dictate whether that A should be positive or negative. So I'm just going to leave it as amplitude equals 2 for right now. We'll decide on whether that needs to be a positive A or positive 2 or a negative 2 in a few minutes. Everybody's good though? Next, I'm going to find the period. So the period is the distance from, I like to do from like minimum to minimum or maximum to maximum because it's really easy to find those points. But any really non-repeating segment would be fine. So that's going from like negative pi over 8 to halfway between a quarter and a half is 5/8, right? Is that right? Yeah, 4/8 is a half, 6/8 is, 2/8 is, that's 3/8, excuse me. So 2/8 is a quarter, 4/8 is a half, in between is 3/8. Everybody okay with that? So that total length for my period then is 4/8 or just pi over 2. We okay with that? And that's nice because I know the period is 2 pi times the absolute value of c. So when I multiply both sides by 1 over 2 pi, I get that c is, or the absolute value of c is 1/4. Okay, so here's what I like to do that I think makes life easier. So anytime I write one of these graphs, if both A and C were negative, I could write the graph or write an answer where both of them were positive. And anytime where C was negative and A was positive, I could also find an answer where A was negative and C was positive. So what I'm going to do is every time I'm just going to fix C to be the positive value. And I'll pick up any negative signs with my A. In my experience, never is there a situation, or I've never encountered a situation where making C negative makes the problem easier. At best, it's the same, and many times it makes it a little bit more difficult. So I'm just going to always pick C to be positive. Is everybody okay there? The most difficult part of this is going to be finding the H and getting the correct sign on A. So the way that I'm going to do this, or the way I like to do this, is I'm going to think about the parent function. So I'm going to pick a point from the parent function. Now it doesn't matter which point you pick, but you can make your life easier if you're able to pick a point whose x-coordinate is 0. And I'll explain why that's true in a moment. So for sine, I know 0, 0 is a point on my parent function. What kind of point on my parent function is 0, 0? Well, let me go back and show this to you real quick. Yikes, that's a lot of colors. So 0, 0 is here, right? That's a midline point. Everybody okay with that? But there's really two types of midline points on a sine graph. This midline point to the left is a minimum and to the right is a maximum. But if I had picked this midline point, there the maximum is to the left and the minimum is to the right. So there's two different kinds of midline points. Everybody see that? Now the midline point that I've chosen here is min, then midline, then max, as we read from left to right, which is how we read a book. And I'm just going to record that information underneath. Everybody okay there? I'm now going to look at my transformed function and find a midline point from there. Any midline point is fine. So I could pick this one, or 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 this one. Any of these would be okay. It doesn't really matter. Everybody's okay with that? I'm going to choose that one because the numbers are the most convenient to deal with because it's a 0 and a 1. That's pretty nice. Everybody's okay with that? Now I need to see what kind of midline point that is. So it proceeds with a minimum and is followed by a maximum. And now I have all the information I need to determine my H and fix a value or fix the sign on my A. Because these were the same type of midline point, that tells me that A is positive. And the x-coordinate here is going to give me my value for H. Let me just take a moment and explain to you why the H is going to be that x-coordinate. So remember that we have this transformation map, right? Everybody remember that? So what this is saying is C times the x-coordinate from the parent function plus H should give me the x-coordinate from the transformed function. So in our situation, I have 1/4 times 0 plus H is equal to 0. this is why it's nice that the x-coordinate from the parent function is 0, because as long as I'm choosing that, the x-coordinate from the transform function is just going to be my h. And there's no algebra to deal with. Now, if you have to pick something that's the x-coordinate from the parent function isn't 0, then there's a little bit of extra algebra to do, but it's like trivial, but like sometimes it can be like you have to deal with fractions or something, it's a pain in the tuchus. So I'm about making my life as simple as possible, so that's why I did that. Does that make sense to everyone? So this is just like a little aside here. So now I had everything I needed, right? So my a was positive 2 sine of 1 over 1/4, so just 4, x minus 0 plus 1. Let's now do the same thing with cosine. For cosine, I'll choose a point from the parent function whose x-coordinate is 0. That's 0, 1. What kind of point is that? That's an extreme point. There's two types of extreme points. There's maxes and mins. This one is a max. So I'm going to go to my transform function now and pick another extreme point. It doesn't matter if it's a max or a min. So I have lots and lots and lots of choices, right? So let's just say I pick, I'm going to pick this one here because I've already identified the x-coordinate for it already when I was doing the period, so it seems like an easy one to deal with. So 3/8, -1. And I observed that that was a minimum. So here, because these were opposite, I know my a is going to be negative. And here, I know that because the x-coordinate is 0, my h is just going to be the x-coordinate from my transform function. Then I have everything I need. Were these the only two answers you could have gotten? No. No, there's like infinitely many, depending on which points you use to find your h. You could have gotten a different answer than me. As long as it's still representing the same graph, I'll be able to tell the difference. If I'm ever unsure, I just graph both of them at the same time and just my answer and your answer, make sure I get the same picture. It's easy to check. You know what I mean, guys? How do we feel about this process? It's a little tricky. It's going to take a practice a couple of times through to get the hang of it, but it's not so bad. This feels like a good place to stop for me, though. So we still have one more piece to talk about, but I think this is probably enough information for one day. The other thing that I want to talk about is going from a description of a graph to an equation. So I won't even give you the picture. I'm just going to give you some attributes from the picture. That'll be the last step here in section 3.1, but we'll deal with that in the next class. To talk about next week for a minute, we only meet 2 times or 1 time in person next week. Monday and Tuesday are real school days. Wednesday and Thursday are virtual days. And then Friday, there's no school. On those Wednesday and Thursday virtual days, my plan, I'm going to give you like a 15-minute video of just me doing some example stuff. I've already made it. It's already posted. And just ask you to continue working on your problem set. So today, you guys should be able to do worksheet 1 quite easily. So all we're doing is identifying some values and then describing the transformation and then doing some graphing on worksheet 1. Should be fairly easily doable. Next time we'll talk more about, we'll do another example of going from graph to equation, and then talk about going from a description to an equation. You guys can work on worksheets 2 and 3. And I have some book problems that correspond to that stuff that I'll assign also. And then Wednesday or Thursday, the virtual day, is basically a work day as far as I'm concerned. Like I have a video, like 15 minutes or something of me doing some more examples of like going from a description to an equation. But if you're good, you don't even really need to watch it. You just work on your problem set. So there's nothing live. You don't actually, there's no Zoom, there's nothing to log into. You get up and whenever you get around to it, you do it. There is no problem set due this weekend, so there's no homework check this weekend. Notice the date on the board for worksheet 1 that I just assigned here today is for the 10th. That's not this Sunday, but the following Sunday. Again, I want to make sure that we have a time in class to talk about or ask questions about anything before I expect it to be turned in. Plus, this seemed like a pretty hectic week for everybody involved, so like one less thing to have to worry about this weekend, and maybe you can find a little bit of me time, you know. Any questions about any of those